So a lot to get through today. We're mostly going to be on chapter 23, where we're going to learn about electric potential and electric potential energy. It ties in a lot to electric fields. And then we're going to probably next week get into chapter 24 and then move on from there. Any questions before we get into things?
Yeah, I noticed that you record the meetings. Is there anywhere we can access those recordings?
Yes, it's posted on Canvas in the extra files. I can put in the chat as well.
All right, thank you.
They are posted here. Anything else? So the
What?
next,
Is this a live class?
the next homework
Yes.
is going to be due on Monday,
Mm-hmm.
and
You're good. It's muted and wait. Sorry.
we're not.
It was muted when I came in and I did not do anything. It just unmuted itself. My bad.
No worries. And on Monday, there will be a quiz using Gauss's law. And the next homework we'll do on Monday, which will just reset our old pattern. For Gauss's law.
You said we have homework this week, Professor?
Yeah, so I'll post it today and it'll be due on Monday.
Okay.
And I'm going to post the solutions to today's homework today as well. So for using Gauss's law, there are a lot of situations where you can use it, but for the situations where it's easy and practical to use, there's the point and the uniform sphere. And in those cases, the end result of working with Gauss's law is going to be 1/4 pi epsilon q over r squared. So just what you get for electric fields from a point charge, same from a uniform sphere. For a cylinder or a wire, it's 1/2 pi epsilon naught times the charge density divided by distance. And for just a thin sheet, where it can spread out in both directions, it is the area charge density 2 epsilon naught. And if you have the area between two sheets or near the bulk surface of a conductor, the electric field is just the area charge density. put that? Oops. So number one had a cylinder of uniform charge density. With a radius of 0.02 meters. But asked for the electric field just 0.01 meters from the center. So you can make a Gaussian cylinder with a 1 centimeter radius, and then plug it into Gauss's law. So we can use our simplified form because our geometry is nice and easy. We just have electric field times area. This form doesn't always hold, but here it's just fine. Where the area is going to be the vertical walls of the cylinder because the electric field is not going to be heading out the top and the bottom. And Q enclosed is just the charge that's inside. Exterior charge doesn't count. So this is going to turn into pi r squared H for the volume of a cylinder. And multiply that by our charge density. And the area is 2 pi r h. Pi cancels. One of the powers of radius cancels. Pi cancels. So the 2 centimeter radius of the larger cylinder actually doesn't come into play at all. It's not enclosed, so it doesn't count.
And the epsilon not, Professor?
Yep. Keep dropping my epsilon knots. Shame on me. Yep, there it goes. And for number 4. Ooh. Yeah, number 4, I think is the trickiest one of the bunch. Cool. So for number 4.
Actually, I was all right, except
There's
for
a spherical shell. And the inner radius was 0.3 meters and the outer was 0.4 meters. So there was a somewhat complicated charge distribution. There was -3 microcoulombs on the shell and a 2 microcoulomb point charge in the very center. So to start off with this one, let's do Gauss's law by making a Gaussian sphere that is, say, 0.35 meters in radius, concentric with this sphere. Magnitude of the electric field needs to be 0 because it's inside of the conductor. No electric field. Therefore, no net charge enclosed. So there needs to be -2 microcoulombs on this inner surface of the sphere. So that negative charge gets drawn closer to this positive point charge in the middle. It needs to be that way for us to get no electric field in our conductor. And if there was a net charge of -3 microcoulombs, and we've got -2 on the inner surface, well, the other charge needs to be on the outer surface. So it's going to carry -2 microcoulombs on the inner surface and -1 microcoulomb on the outer surface. That's the only way to get exactly no electric field anywhere within the volume. So then it just turns into the surface charge density is the charge that's on any given surface divided by 4 pi r squared for the surface area of the sphere. That gets you to the answers for 4. Okay. And I will post it with numbers at some point today, but that's the how it's done, which I think is what's more important. Let's get to electrical potential and electrical potential energy. There's a positive charge. There's another positive charge. They are brought closer together. They're repelling as that is done. So if you push things together that repel each other, it's hard to do. You need to do work to make that happen. And after they were brought close to each other, if they were released, they would fly outwards. So there would be some release of kinetic energy because you did work, you let it go, they start moving. So when they're close together, there is potential energy, the ability to do work. It took work to get them there. And the fact that they're close together means you can get work out of them as they fly apart and push things as they go. So there is an energy associated with them being close to each other. Just like there's an energy associated with big things being at high altitudes or strings being stretched. It takes work to do it, and you can give work back as it returns to its original position. There is a potential energy there. What counts as close together? Not infinitely far apart.
Oh, I'm sorry. Did not realize I was not muted.
So the closer they are, the more energy there is associated with it. But if you have two protons a kilometer apart from each other, there's still some potential associated with that. There would be less potential energy if they were 2 kilometers apart, but still some. So any finite distance. At a certain point, it becomes negligible, but we can still do the math and calculate what it is. So just for ease of looking at it, let's just keep one of them fixed and move the other one. So work. Is f.d. Or if we're being simple, it's just force times distance, so everything's perfectly aligned. But the force is equal to k, or 1 over 4 pi epsilon naught, times the product of the charges divided by the distance squared. So as it gets closer, the force gets bigger and bigger. So it's not just a simple product of what the force is now times how far it was pushed, because the force varies with the distance. But it does sound like a job for an integral. Let's do that integral. So we could have any starting point and any stopping point. So just for being general, we can look at it from just a starting point of arbitrary point, finishing point of arbitrary point. The standard when looking at potential energy from charges, which is usually followed, is 0 is all charges are infinitely far away from each other. That's usually where we set 0 to be. But for just a change, we're just going to big and integrate some starting radius to some finishing radius of our force dot dr. Where I'm making things simpler by saying we're not taking this path. We're just taking the straight line path. It doesn't end up making a difference. Because moving around it in a circle does no work. It's conservative, so any path that you get there will be the same. So what we end up getting Q1, Q2, and a difference of our radii. So we get minus. And if we have our A go to infinity, so if we started infinitely far away, our work. So this is the potential energy. This is the work that we needed to do to get here. So K, Q1, Q2 over R is our potential energy. So this is different from our force equation. It still depends on the product of the charges on our constant K or 1 over 4 pi epsilon naught. And it does depend on distance. But instead of depending on distance squared, it's just distance to the first power. Or inverse distance squared, inverse distance to the first power. So as it gets closer, you get more and more potential energy. And if you let them be points, you still end up with the divide by 0 problem if you want to set your distance to 0. But it is less strongly dependent on distance than forces. And this is just for 2 points. So this work. Can I go back? I think it's gone forever. Oh, nope, it's back. Cool. So knowing this, how much potential energy would there be if we have a 0.005 Coulomb charge, 0.05 meters from a single electron? And going with the conventional way of setting infinity distance between them is 0 potential energy.
do we get a negative because they're oppositely charged?
Yes, you do. So this is a negative potential, which if you want to lose sleep thinking about, feel free. Or you can just look at it as it's not about potentials being positive or negative. It's about them being different from what we said zero. So it would take work to get these to the point that we said zero. So this is a lower potential than that point we defined to be zero. So yes, it is negative.
I'm gonna assume due to the units of K, we still get joules out, right?
Yep, it all works out to joules.
Marvelous.
So our potential energy. It's going to be squared newtons coulomb squared times 0.005 coulombs times minus 1.6 times 10 to the minus 19 coulombs over 0.05 meters. And just doing our analysis of units, coulombs, coulombs, will cancel coulombs, coulombs. Meters cancel 1 power of meters. And we were left with meters times newtons, which is the same as a Newton meter, which works out to be joules. I got minus 1.44 times 10 to the 10th. I'm sorry, 10 to the minus 10th. Just an electron, not a lot of charge there. An electron is negative the elementary charge, correct? So what if there is more than 2 charges? That is a thing that can happen. Sometimes the universe has more than 2 charges in it. You can figure out the total potential just by looking at every pair of charges. So if we've got positive charge, and a positive charge, one way of looking at it is this positive charge started there. And then we needed to bring in this one. So that needed to do work getting close to the first one. And then we brought in the third one. And that needed to do work against the first 2. So we end up needing to count the interaction between every pair. So the potential of any one charge being there is the potential from each pair it interacts with, but the total of the system is just the sum of all the pairwise interactions. And if there are more than three, we can just express it as a sum. So any idea why we do the sum over I greater than j instead of all I and j?
Is it because you're not starting with the first one? You're starting with the second's interaction on the first one?
That's part of it, because we don't want to count charge 1 times charge 1 divided by the distance between charge 1 and charge 1. That would blow things up right off the bat. So making sure that I is not the same as j, that we don't count the interaction between charge 1 and itself, an important starting point. The other one is it just stops double counting. We want to count each pair once. So if you counted the interaction between 2 and 3 and the interaction between 3 and 2, you'd count everything twice. So this is just a way of getting to here, but counting each pair only once. So that's how much energy it would take to assemble a collection of point charges. And this is just, the second way is just a fancier, more compact way of expressing what the first one's saying. So we have so far learned about force, and then there was electric field. Which is force per unit charge. And we have potential energy. And we have electrical potential. Which is potential energy per unit charge. So a lot of the mental steps that we took getting from force to electric field, we can take on our path from potential energy to electrical potential. So electrical potential, it gets a capital V, and it is measured in the volt. Voltage is a very similar idea to electrical potential, extraordinarily similar, that they're sometimes used interchangeably, but they're not quite the same. Voltage is differences in electrical potential, is the proper way to use voltage. But same big idea. Difference in potential energy per unit charge. So if this would be measured in newtons, we have newtons per coulomb as a way of measuring electric field. This should be measured in joules. Joules per coulomb would be a way of measuring this, or volts. So it also can be measured in volts. And it is, you can call it good or bad, that the unit for measuring voltage is the volt. Either easy to remember or confusing over reliance on one word. Whichever you think is correct. But yeah, measured in volts, which is the same as a joule per coulomb. So it's just how much energy is there per charge that you could put at this point. So forces required 2 charges. But when we move to our looking at it from an electric field perspective, the electric field is a property of space, that there would be forces on charges in that space, whether or not you actually put a charge there. So a given test charge in that spot would get a certain force per unit charge. Electrical potential is similar. In order to have potential energy, you need interaction between 2 charges. But a single charge can change the area around it, such that you would need to do work to put a test charge there. So it's a property of the space near other charges that in order to put charge there, you would need to put energy. So that area is at a high electrical potential. So just going back a little bit to our work analogies, if we have a positive plate near a negative plate, our electric field goes from positive to negative. And if we make a free positive charge in space, it would get pushed along. So because it's in an electric field, it experiences a force. And as it went moving along, it would be getting faster and faster, gaining kinetic energy. So it must also be losing potential energy. So near the positive plate, it has high potential energy. And because it's a positive charge, we call that place a high potential. As it gets close to the negative plate, it has lower potential energy, which means it's a spot which has a low electrical potential, because positive charges have low potential energy when they're in places of low electrical potential, and high potential energy when they're in places of high electrical potential. So our work. just give me your force times our distance. If everything's in a straight line and unchanging, our force is charge times electric field. So the work will be charge electric field distance. Our change in potential energy is going to be minus the work done by the field. So if we just define electrical potential at a point as being equal to potential energy at that point per unit charge, our change in electrical potential, which is going to be our potential at point B minus our potential at point A. And these should be more angular letters, just to be clear that they're not U's. So how much our potential changed? All should be more angular. So our voltage or our change in potential is how much our potential energy changed per charge that was moved. Or minus how much work was done per unit charge. So this also can be expressed as looking at an easy way to figure out how much our potential energy changed. It's equal to the charge times the change in electrical potential. So moving a charge to an area of higher potential is going to change the potential energy of the system. Moving it closer to the positive plate would increase its potential energy. So this example had a positive charge. If we had a negative charge, it would, if released, move towards the positive plate. So the electric field does work on it as it moves to areas of higher electrical potential. So same idea, but you just plug in a minus sign for the charge. So it gets pushed into areas of higher electrical potential, and positive charges get pushed into areas of lower electrical potential. The electric field electrical potential relationship is quite strong. Because our change in energy is our integral of force, our change in electrical potential is going to be the integral of force divided by charge. So if And this works because our electrical potential is energy per unit charge, and our electric field is force per unit charge. So we just take our relationship of our change in potential energy is the integral of work, and divide both sides of this equation by charge. So force divided by charge becomes electric field. Change in potential divided by charge becomes change in electrical potential. So this is true in general. If electric field is constant, the integral of electric field over distance just becomes electric field times distance. So in that special case, it's just product of electric field and distance gives you the change in electrical potential. So between those two parallel plates where the electric field was constant, you could figure out the voltage between them, knowing the electrical field and the distance you had to travel. Let's work with this a little bit more. If you have 4 charges in a square, how much potential energy would that take? So remember to count every charge pair once. So you have 4 things. Oh. A square with 1 meter sides. So how much energy would it take to arrange these? They started infinitely far away. So how many pairs are present? A lot of the pairs are going to end up being exactly the same. So we've got the ones where you've got a pair of these charges that are 1 meter from each other. And we had 4 of those. And there are 2 other pairs. Diagonal pairs. And those are √2 meters from each other. So the nice thing about switching to electrical potential as how we're looking at things, instead of electric fields or forces, is that electrical potential is a scalar, not a vector. So when you add electrical potentials together, they don't add like vectors, they add together like adding 2 into 3. Just add them up. So it's going to be the sum of our pairs, which I'm just going to collapse real lazy. So we've got 4 pairs that are a meter apart. And 2 that are √2 meters apart. And plugging in all the numbers, I ended up with 4.87 joules. Questions on this one? So different question. If you wanted a potential of 1 volt, how close do you need to be to a proton in order to find it? Again, assuming 0 volts is infinity. the equation. Is our electrical potential equal to K Q R.
Your units, I think, are upside.
Yeah, I flipped this over. Usually I get epsilon wrong upside down. This time I got epsilon not upside down. I use my epsilon not units for K. There we go. And now my units are all happy. And I do end up with meters for an answer. Which is not that far off from atomic scale. I would have gone for 10 volts. You get atomic scale. It's around there. So kind of interesting that the electrical potentials that you would see in an atom are in the neighborhood of a few volts. Kind of neat. So chemical things can make things happen with potentials in the neighborhood and energy in the with changes with energy per unit charge of things in the neighborhood of a volt. Electric fields are not always straight lines of uniform strengths. And electrical potentials don't always change uniformly because of that. So just like drawings of electric fields can get more complicated, we can make drawings of our electrical potentials. So if we go back to our nice simple case to show how things are working when things are simple. We've got positive plate and a negative plate. Our electric field. Go pretty uniformly from positive to the negative. Everywhere on the positive plate, if we let it be metallic at least, should be at the same electrical potential. if there was a spot that an electron would rather be or would get pushed to not turn our electron into something with actual wants, it would move there. So everything must be at the same electropotential. There are no electric fields in here, so there's nothing to do work on something as it moves through it to make it end up at a different potential energy. So it's all at the same electropotential. Same with our negative plate. But moving between them, that's definitely not the case. So just picking, if we set this to be at 0 volts, and if it say took 20 joules to move a coulomb from here to here, this would be at 20 volts. And there would be a map of places be at 10 volts. Or 5 volts. Or 15 volts. The lines would ideally be straighter than I drew them, but you get the idea. Where everything along one of those red lines is at the same potential as anything else on that red line. So the closer you are to the positive plate, the higher the electrical potential. The more potential energy there is for a positive charge to be there. So at all those points that are at that same distance, they end up being at the same electrical potential. So this surface that I drew is called an equipotential surface. So it's just a set of points that are at the same electrical potential. And in the drawing, those lines of constant voltage are always crossing the electric field lines perpendicularly. And that is always the case. Electric field lines point the fastest way to change your electrical potential. And these equipotential lines are the direction of no change of electrical potential. If we had just a point charge, instead we wanted to look at a map like this. Our electric field lines would go radially outwards. And I already showed that the electrical potential has a 1/r relationship. So it's just the distance that determines the equipotential lines.
Professor, I've got a potentially dumb question.
All right.
So in order for you to harness this energy, this potential energy from positive to negative, there has to be, albeit very small, it has to be like a physical space between the two plates, right?
Yes.
So if you were to plug, like, for example, let's say a motor into an outlet and try and harness the power of it trying to go from positive to negative with your two prongs, where's that space on the motor? Is it like in the brushes or something?
So most motors are using magnetism in addition to flow of electricity. So it's not just an electrostatic thing going on. You absolutely could make a motor that was just relying on electric fields and not magnetism, but usually motors, you need magnets also in order to make them work. So they're operating as more complicated things.
What about like a light bulb? Because it seems like light bulbs have a wire where the thing just flows through and there's no gap.
Yeah, so for your simple incandescent light bulb, there is electron flowing, and a simple model for that would be, instead of getting work out, it's an electron flowing through something with some resistance. So it's a lot like a box sliding over something with friction. So it's moving to a lower electrical or a higher electrical potential if it's a negative charge, or a spot with lower potential energy. But it's moving through something that resists its flow, not a perfect conductor. So it's like something sliding downhill over friction. Work is done on it, but instead it heats up its surroundings, and the energy is released as heat and light if it gets going fast enough and hot enough. So that's the principle of an electric heater or an electric incandescent light bulb.
That makes sense. Thanks for explaining that. It's finally starting to click with real things.
Good. Yeah, I should put in more of those. Yeah. So equipotential always perpendicular to our electric field. And yeah, if things move to lower potential, it's not always going to end up as that energy that's free. Sometimes it turns into heat. So this is another way of mapping what's going on with a system of charges. You could make a map of something's electric fields. But if you know the shape of the electrical potentials, you could figure out the electric fields from it. And if you know the electric field shape, you can figure out the electrical potentials from it. So something to help that visualization. So I think we've seen this one before. If we have a positive charge, electric field lines go away from it. Negative charge, electric field lines bend towards it. But instead of looking at the electric fields, you could look at the electrical potentials. And as you move from red to blue, that's the direction that electric fields take. If you make a arrangement like this, you can see a lot of the same pattern, where as you are moving away from red and into blue, that's always the way the arrows are going to be pointing. So once you have one map, you can figure out what's going on with the other one. Pretty well. An analogy that I am very fond of is looking at it in terms of a topographical map. So you can think of the electric field as the direction downhill. So you could give someone an idea of what the terrain is like by just drawing in a bunch of arrows which point downhill. You also could get there by showing all the lines that are at the same height. So if you are not familiar or not a fan of topographical maps, that's unfortunate. They're a lot of fun. But our big idea is if you have hill near a big hill, and you made a map of this, your map might look kind of like this. And you might be at 100 meters. So every point that is 100 meters from the ground is drawn in, and every point that's 200 meters from the ground is drawn in, every point that's 300 meters, and every point that's 400 meters is drawn in like that. So the map gives you a picture of the land. And you could do the same thing with electrical potentials. If you had a bunch of positive charges, the area near them would be at a very high electrical potential. So if instead of thinking about hills, we think about just a map of equipotential lines. It's going to be something like that. So there's our map. So I would like to consider certain points on this map. Points A, B, C, and D. And for our simple checking question, where at each of these points would there be the greatest electric field? Just greatest magnitude, not worrying about the direction. Would a charge receive the greatest magnitude of acceleration? And this one is tricky. Our answer is not C. So electric field and high electrical potential are not the same thing. It could be point C. It's hard to know what's going on at exact point. Could be. It's hard to say. I was going for B, which clearly has a strong electric field there. It's hard to know exactly what's going on at point C. If it was the curved top of the hill in the original drawing, then there actually wouldn't be an electric field at point C. So electric field is not the same thing as electrical potential. Electric field comes from the change in electrical potential. So if we go back to looking at this as a topographical map, it becomes, what's the steepest way downhill? That's where the strongest electric field is. If you have to quickly move from 3 volts to 4 volts, 2 volts to 10 volts, that means a short change in distance has a big change in potential energy or electrical potential. So that's a steep downhill in geographic terms. So our electric field map would go like that. But if you have the same change over a short distance, that means the electric field needs to be quite strong. Right. Let's
So
look at a. Oh, go ahead.
Which one has the greatest electric field or the strongest? Which one?
B.
All right.
You could make an argument for C because it's hard to know the details of that point. I wanted it to be a rounded top, but there's no proof that it is. But things change rapidly at B. A small change in place has a big change in electrical potential, which is like having a small distance taking you to a very different elevation. So things would physically be pushed downhill very quickly in that area, and charges would be pushed very quickly away from the positive charge in this area. And where would an electron have the most potential energy? And this one's tricky as well because electrons are negative. So electrical potential is how many joules there are per coulomb. So a positive charge would have the most potential energy at a high electrical potential, so point C. A negative charge would have the most potential energy at a low electrical potential, so point A would have the most potential energy for an electron. So just like force and potential energy are not the same, electrical potential and electric field, not the same. It's tied into the change. So if our change in electrical potential can be expressed as the integral over the electric field, so integrating over the electric field gets us to our change in potential. If we just think of taking the derivative of everything here, or our electric field is just the derivative of our electrical potential over space. So the faster the electrical potential changes over space, the greater the electric field is there. If you want to make this all super vectory, this works for each component. Where my curly symbol I wrote here is my partial derivative symbol. Just how the electrical potential changes with changes in x coordinate gives you the x electric field. So in other words, if moving in the x direction causes you to end up at a higher potential, that means there is an x component to the electric field. And due to this minus sign, it would be a negative x electric field. If moving in the y direction caused you to get to a higher electrical potential, then there would be a minus y component to the electric field, and so on for z. So the spatial derivative of the potential gives the electric field. This does help tie us back to the idea of it only being differences in electrical potential that matter, because if we increased the electrical potential everywhere, uniformly across space, said everything that we used to call 0 volts, we're now calling 1 volt. Everything that we used to call 100 volts, we're now calling 101 volts. That wouldn't change its derivative over space at all. So that would mean the electric fields would be the same as they used to be. And electric fields are what really move the charges around. So it's just the differences that matter. All right. A lot of ideas. Let's do a little more work with them. It's too much. Right. So we've got a sphere. And it's metallic, so this charge that's on it is going to be uniform over its surface. So what would the electrical potential be if you're near the sphere but not inside of it? See if you can work it out. Remember, by Gauss's law, the electric field of a spherically symmetric distribution of charge is the same as a point charge. So they'd make the same electric field. And we can set uh, 0 volts will be infinite distance away. So if we can treat it like a point, it's just going to be KQ over R. So if we're outside of the metal sphere somewhere, our distance from the center is what matters. And our units, we have Newton meters squared per Coulomb, or joule meters per coulomb or volts times meters. And that's because we've got our hidden power of meters in this radius here. So the closer we get to it, the greater the electrical potential. All right. The next one is very, very similar, but there's a pretty big trick on it. What if instead of looking at the electrical potential on the outside, we were looking at the electrical potential on the inside of that same sphere? So starting off, what would the electric field look like on the inside? What would they look like on the outside? This one's weird. I'll let you think it over a little bit. So for our electric fields, the closer, oops, those directions were wrong. Away. The farther from the sphere, the weaker the electric field gets, and it should be going away. And on the inside, nothing at all. So to make a graph of this, our electric field against distance, it has a 1/r² relationship. But inside, there's nothing. This is at 0.2 meters. So the electrical potential will have that 1/r relationship on the outside. And no electric field doesn't mean no electric potential. It means no change in electrical potential. Zero derivative or spatial derivative. So if you just figure out what the electrical potential is at the surface, then you know the electrical potential at all points on the inside. Because it's metal, it all should be at the same electrical potential. So if we just need to plug in 0.2 meters. And get 1.44. And as long as R is less than 0.2 meters, there is no R dependence at all. So inside of a conductor, no electric field, ideally. And there can be a non-zero electrical potential. It's just always going to be the same non-zero electrical potential at a given time inside of a conductor. All points of it should be at the same potential. Because if they weren't, charges would just flow until they weren't. So there are electric fields from point charges, and then we figured out we can do distributions in addition to just point charges for electrical forces and electrical fields. We can do the same for electrical potentials. So if we're not dealing with point charges, we can move on from adding things up to integrating over them. So for just a point charge, and if there are multiple point charges, then our electrical potential at point A is equal to the sum over all the charged particles of the electrical potential due to that point or 1/5 pi epsilon naught, also known as K, times the sum of what the individual charges contribute, which is their charge divided by their distance to point A. Which is again a bit easier than finding the electric field from a distribution of charges because we don't need to deal with the vector nature. If we don't have a countable amount of charges, but we're just thinking of it as a fluid-like distribution of charge, a line distribution, an area distribution, or charge distributed throughout a volume. Our potential instead of being a sum over charges would be an integral over charges. And this could be, a triple integral over a volume if life was hard, or over a surface, or just a line. So for a not so bad example of this, let's go back to our ring. So we had something like this on homework, but going for an electric field. If there is a ring, and I want to know the electrical potential above the ring instead of the electric field above the ring. We can just integrate around the ring and figure out how each bit of charge there changes the electrical potential at this point. So our electrical potential at that point at the top there one over 4 pi epsilon naught, the integral of dq over r, which is the same as I'm going to make this a capital R, just so I don't have two variables for the same thing. So the distance between any bit of charge and the point we're making our measurement comes from the Pythagorean theorem, square root of h squared plus capital R squared. And then we just need to integrate over dq. So for problems where different charges were at different distances, we could not pull our distance bit out of the integral, but this time we can because all of the charge is this hypotenuse away from the point we're measuring. So we just need to figure out how much charge is there. So this is or if you instead had a linear charge density, that total charge would become 2 pi r lambda. So still not easy, but I think easier than finding electric fields because the vector bit, you just don't need to worry about it at all. So for this solution, if the height becomes very, very big compared to everything else, the potential goes to 0. And if R becomes very, very big compared to everything else, it just becomes 2 pi lambda over 4 pi epsilon naught. So it could be done over a surface, over a volume. I'm not going to do too much of it just because it's, I guess, more math than the fruit is worth most of the time. An interesting case is what you get from a dipole. So if something is not super close to a dipole, being very close is going to throw off our math a little bit, but still in the neighborhood, close enough to matter. If you're trying to get the potential from being near a dipole, it's not necessarily zero because you can be closer to one charge than the other. So it's this difference in distance that's going to give us our potential. This is approximately right angle. So our electrical potential is going to be K times the sum of our charge over our distance. So we have R1 and our larger R2. So looking at our positive charge, we can just call that R, and this will be delta R, this bit here. So the potential from the positive charge is just going to be K, Q, R1. And the potential from the negative charge is a negative Q to balance out our dipole. Divided by R1 plus delta R, that little extra bit of distance. Doing some algebraic manipulation on it. So if we just cross multiply our terms, 1 over R1 and 1 over R1 plus delta R. We end up with delta R for this. And most of the time, if you are close by to a dipole, you just have to stop here. However, if the length of the dipole is much, much less than the distance from it, we can make some useful approximations. Where this extra bit of length here is just going to be L cosine of theta. And R1 plus the change in R is close enough to approximate as R1. So Q times L, that's just our dipole moment P. So the potential energy associated with, or the electrical potential near, but not too near to a dipole, relates to the dipole moment, the angle. So how much, how is it oriented? Is it 100% aligned so that you're over here, and that cosine term would give us a 1? Or is it over here where you're equidistant from the positive and negative ones, and we get a 0? Or over here we get a -1, close to the negative term? But it has a 1 over r squared dependence instead of a 1 over r dependence. So the forces had a 1 over r cubed instead of 1 over r squared. So the effect of a dipole falls off faster over distance than the effect of a single charge. Yes, it could be. I'm using this as assumption that R1 is approximately R2. So the distance to the close one, the distance to the farther one are about the same. So I moved from this line down to this line. One of the steps was assuming that R1 plus delta R is the same as R1. So you could call it the distance to the closer one. Usually you just call it, the distance to the middle, because I assume they're close enough just to smear it out and call them the same.
Professor, that delta lowercase r, is that supposed to be lowercase, or is it should it be something else?
Delta lowercase r.
On the second from bottom line?
Here?
No, the one on the top of that fact. Yeah, I think I can actually. I don't think I can edit on this. You see?
Oh, this. Oh,
yeah,
oh,
that
yeah.
one.
Oh, yeah. That
the numerator.
there it is.
Okay.
Yeah, that I was not making a distinction between upper and lowercase r's. Yeah, that was ugly. I should be consistent. Yeah, delta capital R to stay consistent. There we go. Cool. So there was a lot today. Electrical potentials and electrical potential energy, they're important. We'll work more with them next week as we get into capacitors. And this problem had no rows in it. Yeah, just a change in the difference in distance was what I was going for. Oh, yeah, the dipole moment P. P for dipole moment. Where that's just the product of Q and L. What happened to negative Q from the second line to the third line? I guess there was several algebra steps going from the second line to the third line. It turns into KQ 1 over R1 minus 1 over R1 plus delta R, where I should be consistent and just keep this capitalized. Then cross multiplying. And then bringing them together. So we've got a plus R1 and a minus R1. So all that lives is delta R. And on the bottom, R1 plus delta R. So it was just several algebra steps, and I didn't show all of them. So that's totally fair to ask for that to be shown again. So Monday, there will be a quiz on Gauss's law and some homework involving electrical potential energies. Right. And that'll be it for today.
Okay,